Okay, so let's look at similarities or symmetries, complex analytic symmetries of H and D. Okay, and I'll be using whichever is convenient, freely passing between the two, but mostly it will be H. So what are the symmetries of Z? H. So some symmetries, it helps when we talk about the symmetries, of course, to have a picture in mind. Well, first of all, you have Z goes to Z plus A real number. These are just translations, but A has to be real, otherwise it won't preserve the upper half plane. But so long as it's real, you're just preserving the real line. A second class of symmetries is Z goes to Kz. Again, K is greater than 0, which implicitly in complex analysis means it's a real number. This means you're scaling things. So here's the origin. So Kz is just scaling things out like this. And the third symmetry, little less obvious, Z goes to minus 1 over Z. Okay, you have to put this minus 1, otherwise it will take the upper half plane to the lower half plane, the reciprocal. Okay, so these are all symmetries of the plane, and so composing these, well, if you look at compositions of these for various A's, K's, etc., you get exactly things of the form Z to AZ plus B by CZ plus D, with A, B, C, D real numbers. Okay, and the determinant AD minus BC, I shouldn't put mod here, simply AD minus BC. Okay, this itself is a fascinating story. What is the relation between fractional linear transformations and complex analysis? But I'll just not talk about that story. Assume that this part of the story is familiar to everybody. So we compose these, you get these, and of course here the theorem is that these are exactly the biholomorphic maps. Now we have a corresponding description on D which is quite similar. I won't give that in detail because I really won't use it. I'll just use specific symmetries of D where they are more visible than the corresponding one. So here are the symmetries, and recall our question. Question is there a distance that is preserved by these, and if so, what is it? Okay, so let me just say what kind of distance here. Obviously, I don't mean just Euclidean distance, but let's not look for arbitrary metric spaces. Okay, so in Euclidean distance can be given, of course, directly by a formula, but instead we can look at Euclidean length. Okay, so suppose gamma mapping say 0, 1 to R squared is smooth. The length of gamma is the integral of from 0 to 1 of norm of gamma dot of S ds. Okay, now I'll also have another quantity, energy, just to illustrate things, is just E of gamma is integral 0 to 1 of norm of gamma dot S squared ds. Well, energy is nicer because it's quadratic. Yeah, everybody knows that quadratic things are nice. So I can write it as the inner product of this. Okay. So what we do is, this is the Euclidean formula. We look for a metric obtained from an inner product at each point. Okay, fine. So that is to say we have an inner product at each point, and we want length of gamma to be the integral from 0 to 1 of norm gamma dot of s h. Okay, and maybe for now I'll put for emphasis this depends on the point gamma of s ds and distance is shortest length, more generally infimum of length. Okay, but it will turn out to be the shortest length. So let me clarify here, rather than taking an arbitrary distance, what we are taking is what's called a Riemannian metric. That is, we assume that we have a measure of length at each point. Okay, that is an inner product at each point, which gives you a norm at each point, and we integrate that to measure lengths of paths, and the distance we are concerned with is going to be the minimum distance between 2 points, where we minimize over all paths. Okay, so this is the story so far. We want to know the length of gamma is integral of 0 to 1 of gamma dot of s. Yeah. So we want this kind of distance. Just some side remarks. Well, of course, we could look at completely general metrics, or we could look at metrics coming from norms and not require those norms to come from inner products. That's called a Finsler rather than Riemannian metric, which is also important in certain situations. But right now, let's say that our metric comes from the an inner product, which is different from the Euclidean one and is different at each point. Okay, so if each point is a distance.